I want actually just to take a minute also to first, of course, thank the organizers for inviting us all here to this marvelous place with perfect weather. It's already, with global warming, winter in Sao Paulo is actually perfect weather for us coming from Europe. The other thing, of course, is in contrast to everybody else, I did not take the famous many-body physics course, so I don't have notebooks full. And actually, my interactions with Eduardo were purely, actually, I should say, social, because, of course, we interacted a lot with his thesis advisor, who was sitting out, I guess, in Aspen this morning, greeting us, and we've basically been together at a lot of conferences. I only remember one, and I don't want to go into too much detail here, is I think where we discovered room temperature superconductivity in Brasilia. In particular, it was actually very well, we didn't see the Meissner effect, but we did see zero resistance. But I think we'll leave that topic for after dinner tonight. But I think we've really I've enjoyed interacting with Eduardo. And actually, there are some problems, particularly 1D spin chains, where actually there's even some intellectual contact. So happy birthday. And as Pierre said this morning, 60's the new 40, so don't worry too much. Good. So I'm going to talk a little bit about something that may seem unrelated to the things we've been talking about at this meeting, but they involve a lot of the same skills. And this is really the problem of imaging intelligence, and better than GPT, hopefully, we saw this morning. It's essentially trying to establish the connectome for both natural and artificial brains. And this is work that I started in Switzerland with a very, very talented set of people, particularly the two individuals here at the top, which is Mirko Holler, who's basically the hardware genius, and Michael Oschel, who is a software genius, and you'll see quite soon why you need both of these in the experiments that we've done. There's a large range of other people, mainly at the Paul Scherrer Institute, but also at the University of Southern California, particularly people from Tony Levy's group, who've been instrumental in pushing us along this road. Okay, so these are, of course, the icons for intelligence. Have Intel chip on one side, and of course our brain on the other. This is getting, and of course what's inside Intel and what's inside our brains essentially are networks where basically the bottom are these switching elements. In the case of electronics, it's the transistor, and that's just a typical schematic of a FinFET. And in biology, of course, it's the synapse, which is the biological transistor. Of course, the functionality of these things does not really follow immediately from looking at those devices. The functionality follows from the networks. And that's true, again, both for the brain, but of course also for the integrated circuit, which is shown below here. And so the big quest here is to understand these complex networks, both the brain and actually also the complicated electronic circuits, on all relevant length scales, starting off from the smallest fundamental unit, the transistor or the synapse. And it's really remarkable, of course, the brain, is something which is sort of a, if it's, it's of order of a fraction of a meter, and the synapses are down at 50 nanometers. Chips are a few millimeters. Transistors are in the 10, 20, 30 nanometer range. So it's all of this, both machine intelligence and natural intelligence, is based on a multi-scale, very multi-scale, many decades, 8 decades of length, organization of some kind of a connectome. And of course, how do we see it? Of course, it's very easy for us to see things at the 1 meter level. because we have eyes and brains connected. So since the days of Adam and Eve in the Garden of Eden, we've been able to see some forms of intelligence. Of course, at the 1 millimeter level, we're very familiar with all kinds of brain imaging tools in hospitals, like magnetic resonance imaging. And then at the synaptic level, things get a little bit more interesting, but we know in detail, extreme detail, because of X-ray diffraction and electron microscopy, the relevant proteins that exist at the switching proteins, which exist at synapses. And then we have some idea from various forms of electron microscopy how these units are actually arranged relative to the presynaptic membrane and postsynaptic membrane. So we use, what's interesting about these slides that I've just shown you is that all of them were generated by some form of light. MRI, of course, is radio waves. That's very long wavelengths. Protein crystals are X-rays. That's very short wavelengths. And then there's all of the stuff in between that you're all very familiar with. But photons really are the dominant tool that we use. Sometimes we also use electrons. But basically, to cover all of these length scales, there's really nothing quite like the photons that we've essentially been, whose ability to see we've actually been born with. Okay, so the tools, of course, that we use, cameras, which are exposed to visible light, MRI, that's with microwaves. X-ray tomography plays an extremely important role. Of course, you've all heard of CAT scans. You've probably had one done if you've had some kind of a medical issue like a broken bone. We actually very recently have been able to image entire mouse brains using essentially classic X-ray tomography with suitable stitching. And this actually works extremely well down to the micron level where we can see, in this case, all of the details of the vasculature. Remember, of course, the brain has a lot of blood in it, which is brought in with very slender veins and arteries, and then, of course, these are an important component, of course, of the working of the brain, because, of course, they bring oxygen to the brain and oxygen to all of this microelectronics, which is implemented naturally in ourselves. And so this is a recent achievement, but this is just showing you on the various scales that we can go down. Now, this is not quite good enough for getting down to these kinds of scales where we actually are no longer able to do tomography, but where we have to now leave real space. Those are still real space images. When you go to the doctor, he's in real space, not in reciprocal space. But actually, at some point, once things get to be smaller than 100 nanometers or a fraction of a micron, you have to switch gears and go from a problem of straightforward imaging to a problem of trying to solve somehow the inverse, essentially to solve the inverse scattering problem. And what I mean by that is, how do we know in such exquisite detail where all of these atoms are, where all of these various protein folds and so on are in the protein database, which is the atlas we use essentially for modern medicine, modern pharmacology. And that we know from reciprocal space probes, such as essentially synchrotrons, basically X-ray diffraction practice at synchrotrons, or free electron lasers. And of course, in Brazil, you have one of the world's leading synchrotrons at Campinas, not very far from here. And actually, one of the key contributions of that synchrotron is essentially particularly distinguished for his contributions to understanding the proteins relevant for agriculture. So we're no longer able to do conventional imaging. I think for an audience of physicists, I don't need to remind you how you image things in reciprocal space and then get back to real space. But in case some of you may have forgotten, of course, what happens is you shine X-rays on some array, could be a crystal, and then there are various diffraction patterns. Of course, you start off with, let's say, the diffraction pattern of some S-wave scatter, which is, again, looking rather isotropic. Oops. On that screen in back of the sample. And of course, as you build up scatters, you then, if you have, for example, a line of scatters, so a one-dimensional material, if you like, you get essentially sheets in a periodic array of sheets in reciprocal space, which are projected onto the detector. And of course, if you go to higher dimensions, you get a diffraction pattern here, just shown in 2 dimensions. Square lattice gives you a square lattice in reciprocal space, which is directly mapped on the detector. If I tilt that, if that lattice is no longer square but distorted somehow, that pattern in K space is, of course, also distorted. And by examining this, and this is something I'm sure you've taught your students, is how to look at such a pattern and go back and figure out essentially what the fundamental translation group is of the material. Of course, you do then this all in 3D simply by rotating the object in front of the beam, and then, of course, you can construct a 3-dimensional reciprocal space image of what you have. Now, this is essentially how these the details of these particular neuroexins actually were found. And of course, to get to these structures, there's one important thing to remember is that the diffraction pattern, of course, gives you only amplitudes. It doesn't directly give you the phases. And so you have to somehow solve this so-called phase problem, which you can do in a variety of ways. One common way is to take advantage of the fact that, of course, scattering cross-sections have real and imaginary parts. You change the energy, for example, of the beam. Those real and imaginary parts change. And then by taking diffraction patterns, let's say for 2 X-ray energies, then you of course have a system of equations which you can solve, and then actually directly solve the phase problem and get back to the electron density, which is then converted into these ribbon diagrams that biologists can then use in their science. So that's X-rays. So what I've now shown you is essentially the tremendous success that imaging has had, both essentially by starting off with visible light and then going somewhat into the X-rays with straight absorption down to, let's say, a tenth of a micron or so to see objects. And so most of biology is done actually with optical microscopy. And I've shown you how you get remarkable information, angstrom level detail information on proteins by going into reciprocal space. Typically you have to crystallize the object you're interested in, so you get the n² advantage from diffraction. And then there's this region, there's this in-between region here, and that's sort of up to the tens of nanometer scale. There's this region here in between, which is actually rather hard to do. It's actually not well suited either to diffraction or to some kind of direct CAT scan. And that is the gap that people fill actually in a remarkably primitive way. So if you're, for instance, interested in measuring the connectome of the brain, you actually have this very simple workflow. First you get a brain, which is of course not always easy for us experimentalists. Maybe you can get one at Campinas when you see Eduardo. But then all you have to do is get a piece out of it. And then you cut it very thin, and then you image it with electrons, some kind of cyanoelectron microscopy, and then you do perhaps some segmentation. But that's now only one thin section that you've imaged. So you have to go back and cut more slices, image those, and then stack those in the computer afterwards, essentially to create a full 3-dimensional reconstruction. So in this intermediate regime, basically what you're doing is you're doing slice and image, with basically very thin salami-like slices of brain, and then trying to reassemble this later on a computer. Very destructive and very time-consuming. Oops, why is this now? This is now decided to, okay. So this is the outcome of actually such a measurement. It's actually got quite nice resolution. This is called FibSem. The thing that you're using to cut, to do the slicing is called a focused ion beam. Basically an ion beam knife that you use to cut. And of course, the ion beams don't make totally clean cuts, but you can write software essentially to correct for that and create these chunks here with voxel sizes of order 10 nanometers. Now, that's not very satisfactory. Interestingly enough, the exactly same technology is used to diagnose integrated circuits. In other words, if you're trying to copy, for example, an Intel chip, what you do is you do exactly the same thing. You get yourself an Intel chip, and then you cut it open, you slice it, and then use these sequential electron images, and then you try to reassemble in the computer. This is really not very satisfying. This actually shows you raw data from such a process, which has not been corrected by any software. And essentially what you see here are, as you go to these interesting smaller length scales, this is now taking an integrated circuit. If you look at an integrated circuit, of course, there's a large number of planes. The bottom plane is the business plane, which contains all of the transistors. Higher planes essentially are there, may contain some power elements and some connectors to address the bottom plane. But in any case, we're very far nowadays from having an integrated circuit being just simply a single or a few layers of transistors. So you have some layers here of transistors at the bottom, and then you have all of this interconnect architecture, which essentially defines the intelligence of the circuit. And things that, when you do this, use this technology here, at sort of the few micron level, things look pretty clean. But by the time you get down to scale bars here below it, the scale bar is 0.3 of a micron. By the time you get down to 1/10 of a micron, you get very significant distortions, which you then have to correct. So this state of affairs is not really very satisfactory. And so the question is, can you come up with a solution to this imaging problem, which is entirely using X-rays? So in other words, trying to go into this forbidden zone, which is between 10 nanometers and a few hundred nanometers, with a technology which is based entirely on penetrating X-ray photons. And of course, I wouldn't be standing here today giving this talk if the answer weren't yes. But there are various paradigms that people have tried. One is actually just to do just try to generalize the optical microscope to X-rays. And I won't belabor this too long, but of course, a microscope depends very much, a full-field microscope depends very much on your ability to make perfect lenses, in particular lenses which you can machine essentially to a very small fraction of the wavelength of the light that's being used. So generalizing, although it's a very appealing idea, and actually people are making good progress on it, is very difficult to essentially implement a standard full-field microscope at wavelengths in the X-ray range, which are a few angstroms. So that's not so great. Another technology, it turns out that even though we can't make good full-field microscopes, you can actually make Fresnel zone plates relatively easily, and you can then also do some kind of scanning transmission microscopy where you just simply go through a sample. Oops. Where you go through a sample and simply scan, let's say, the beam across the sample or the sample across the beam, and just measure, let's say, the absorption as a function of position. And then maybe you can rotate the sample and then do some degree of three-dimensional reconstruction, just as you do for CATs. Of course, this is extremely inefficient, point-by-point scanning like this. And of course, the depth of focus is very small, so you can't really do proper 3D imaging this way. So There's something here, of course, that we're not using that X-rays do, which is that they do diffract. And there's some actually rather special things that happen with X-rays when actually you combine real and reciprocal space. And let me just remind you of some very simple things that you already know. Never underestimate the pleasure you give an audience when you tell them something they already know. And this shows you here just the famous two-slit interferometer. This is what's on the detector. This is as a function of the log scale as you go out on the detector in this plane. And of course, you'll all remember that two-slit interference pattern will give you spots will give you essentially this kind of series of spots. And of course, the spots will be separated on the detector essentially by in proportion to lambda divided by the lattice constant of the material. Okay, so that of course if lambda is very large, then of course the spots go off the detector. If the lattice constant, of course, is very large, of course if the spacing here is very large, of course the things will come very close to the forward direction. But this way, of course, you can measure the distance between 2-point objects directly, as I showed you before when I talked about diffraction. So that's just two-slit interference. Now, another thing that we remember, of course, is Fraunhofer patterns. Same thing here. If I have a slit of width W, of course, I get the series, famous Fraunhofer series. And again, the spacing, I'm sorry that this is a log scale here, the spacing here has something to do with the ratio of the wavelength to the width of this width of the slit. So now I combine these two things. I actually put the objects in the slit, and I calculate the diffraction pattern there. And actually, the diffraction pattern depends, is now somewhat constrained by the slits, because actually if I shift these two objects around within that slit, I get different interference fringes. And so so it turns out that what I can then conclude from this is if I somehow had a slit and I could move, let's say, the objects within the slit, or vice versa, if I had two objects and I moved a slit through those two objects and I took two images, I actually would be able to solve the phase problem there and find out exactly where these two objects were in absolute space. Okay, so in essence, what I'm telling you here is if I combine a bit of real space microscopy with a bit of K-space imaging at each point that I'm probing in real space, and if the spots that I'm using actually overlap, then I can actually solve the phase problem. And so this is exactly what we've implemented now to get into this intermediate regime, this dangerous intermediate regime where I'm operating best in real space, and the other regime where I'm operating best in reciprocal space, I do the obvious thing in between. I mix the two. And of course, now I've shown you the basic undergraduate math. You can now quite easily guess that this can be generalized to higher dimensions. Actually, even 4. I'll show you at the end how you do that. But in 2 dimensions, of course, you collect all these scattering patterns. This is some biological object here. You collect scattering patterns for these various spots. These are corresponding now to the Fraunhofer slit. So I'm moving the Fraunhofer slit across this biological object. And that you see that interference pattern changes each time. But there's overlap. And so because there's overlap, I can actually run essentially an iterative algorithm to retrieve the amplitude and the phase at each point in real space. And of course, I can then generalize this to tomography. I can, of course, take that biological object or whatever object I choose in 3D, rotate it around, and look at all of those images, and then reconstruct in 3 dimensions the full, a full real space picture of scattering amplitude and phase in each voxel. Okay. Now, this all seems sort of very 19th century, so you wonder why we didn't start doing this actually in the 19th century, those of us who were born then. And, but what's really made this possible is you need a very bright source of photons, coherent photons, in the form of light sources such as the one at Sirius that you have, or the source that we have in Switzerland called the SLS. The other thing, of course, that you need are very good detectors with a very large dynamic range. These are detectors we make ourselves. I'll tell you a bit more about them later. And the last thing that you need is nanomechanical engineering. Of course, your resolution is determined by two things. One thing is actually, in this case, the resolution of the instrument is determined simply by how far out in K-space you can count. In other words, the biggest scattering angle defines, of course, the largest Q vector that you can resolve and see in the problem, and you can just invert that, and that gives you the ultimate theoretical resolution. Now, of course, that does you no good if the sample is shifting around, or if you don't know where the sample is, to within the same level of accuracy. So if you have a big enough detector, you can go out to an inverse angstrom, so you get an angstrom of resolution, but the microscopy paradigm that I just showed you only works, of course, if the object that I'm scattering from is standing still on that length scale as well. And of course, in real life, nothing stands still like that. So what you have to do is you have to have feedback. And what Mirko has done is he's built an elaborate set of interferometers, optical interferometers, to actually keep pushing the sample back to exactly the same place in the beam, to within basically nanometers. And there's basically a variety of very clever interferometers. There's the obvious ones, which are planar. But there's another important thing, of course, that you have to do, is that if you're going to do tomography, you have to be able to rotate the sample, but then you have to keep the rotation axis also in a well-defined place in reciprocal space, or in real space, sorry. And there, actually, I'll just skip ahead, this very clever idea of actually not having a planar mirror for the interferometer, but actually having a reflecting sphere, a perfectly machined reflecting sphere, essentially to keep track of where the rotational axis sits in real space, and then correcting that in tandem with what the linear interferometers are telling him to always keep the rotation axis exactly where you want it. And so there's a lot of inventiveness here. I'd be happy, I can talk the rest of the time about that. But of course, there are other things that we need to do. So once you have all of this, you have to get it together in a system. A lot of the biological specimens that we use, of course, are very wiggly. And so if you want to measure, for instance, connectome of a raw brain, which hasn't been fixed, you actually have to keep the sample cold, which is another challenge. So anybody here, again, this is theorist, but has worked with cryostats, and even if you think everything's sitting still, of course it's not. And so there's been a huge mechanical engineering challenge of putting all of that hardware for stabilizing the sample, stabilizing the axis of the sample into a cryogenic environment in this kind of thing. This is actually what the guts of the machine look like. At the end of the day, it's all packaged up in this ultra-high vacuum chamber, which is about as tall as a man. So this gives you the idea of the engineering here that's being accomplished at a nanometer scale science, but then with this kind of very heavy-duty vacuum engineering on top of it. And so the last thing, of course, that I was going to talk about was a detector, but I think the best thing to tell you about the detector is actually what the detector looks like on the inside using our instruments. So the first experiments that we did were essentially, and this is in a very philosophical vein, taking a self-portrait. So we have a detector. We have another copy of the detector, which we chopped up and put on the beam. And here we just simply cut, for this experiment, a pillar out. And then we started to take, why is this not advancing? And start to take images. So this is actually a typical small angle scattering pattern in reciprocal space here. This is a nanometer inverse of a detector chip, of our detector chip. And you can see there's actually some features. That's not noise, those Bragg-like peaks. And what we did was we collected tons and tons of those, and at the end fed all those images, several thousand or over 10,000 images, into our algorithms, and then retrieved basically a three-dimensional image of the detector chip. And let me just show you. So in this video, which is simply a video tour of the data of the three-dimensional data file, where we cut away and see the various layers of the chip, and all the way at the bottom, you can identify all of the business parts of it. You can see the gates, the vias, and this just shows it coming back up again, and this actually segments out for you a single set reset latch, which is actually at the bottom of this detector. And you can, of course, understand that if you're counting photons, you need a lot of set reset latches. This, on the right-hand side, is the actual image, reconstructed image, and that's the circuit diagram that our engineers drew when they placed the order with the foundry. And so this is the self-portrait of that detector. Now, we move on. So this is something where we knew what we had, because it was our detector. There it is. You can, of course, also wonder what's inside Intel. Of course, they will not give you their design file. And so basically what we did was we went down to the shop, computer shop, and simply bought for about 50 francs that Pentium processor. And it didn't say, you know, you buy it, you can do with it what you want. So you can also destroy it, which is what we did. So we simply cut a pillar out of it exactly as we did out of our own chip. And this is what's shown here. And you can actually see it just optically already. It's a 10 micron. You see all of the various layers. And then we stuck that into the beam. And this just shows you just again the paradigm that we're using. Here, this gray area is where the chip is. This is the optical image actually from the side, because we of course have an optical camera on the instrument, and then this is showing you the beam. Basically, what you see here is the interference fringes from the fact that this is essentially a Fraunhofer beam. And so we're moving that Fraunhofer beam across the sample, and these points here, all the grid points here, we simply inspected the small angle scattering. And there's some amusing things that you can do. I don't have time right now, but you can actually look at the raw data. You can see immediately that this chip has a very different architecture than the chip that we made ourselves. What's interesting here, immediately anybody who knows about low-dimensional physics says, oh, this looks very much more like a low-dimensional system than our chip, which looked more three-dimensional. So there's a lot actually you can learn just by looking at a single image. But let's not do that. Let's just keep going. We took tons of these. Actually, you can also look at, you can actually identify these quasi-Bragg peaks here and identify that spacing turns out to be 0.02 inverse nanometers. It corresponds to a regularity which actually you can then see in the chip itself. And so at the end, we did the same thing and reconstructed a chip where we had no idea what the design file is, and in fact, we would probably get shot if we had it, but of course we could recover it simply with X-rays. And this now takes you through this actually much more complicated than our own chip Intel processor. And again, what we're doing here is we're coming down to the bottom, which is where all the transistors live. And actually here you can see actually the individual FinFETs that are essentially the hallmark of this type of advanced integrated circuit. So, let me see if we can. So that's just a still picture, the bottom of it. And here is just now some comparisons with the unprocessed data that you will get from the old technology that I showed you at the beginning of the talk. Remember, I showed you what happens when you use this brutal slice and image routine, and this shows you how clean actually these images get. Down here you actually see the individual FinFETs. And now, of course, the sectioning is done in software. I don't have to cut it out. I have this huge data set, and I can simply cut and slice afterwards to my heart's desire. And of course, this is why you need, in addition to the hardware guys, you need the software guys to do this. This shows a lot more detail on that. I'm not going to belabor this, but you can learn essentially all about the design and even the types of materials that were used to implement this particular technology. And sort of at the bottom, of course, is what I showed you at the beginning, is you can see the individual multi-gate, basically multi-fin or FinFETs, which are bridged by a single gate. Now, of course, what I showed you today, how much time do I have? Somebody keeping? Okay, good, yeah, okay. Of course, I said at the beginning that, you really prefer to, we want to compete with this other technology, which is slicing. Now, what I showed you so far, of course, was much better than that, but we're still cutting out a pillar. And it also it means that we have to make some choice in where we cut that pillar in the chip. You may have only one chip, and then if you cut one pillar here, then it's going to be hard to cut pillars next door. So we have to, and there's a reason why we have pillars is that cylindrical symmetry is enormously advantageous if you do any kind of tomography. And actually, it's lucky that for hospitals that people, especially if they're, people tend to be cylindrical or spherical. And so what we really want to do is entire chip inspection without any bias brought in by selecting a pillar to cut out. And this is a very hot issue because the normal, particularly in recent years, because of course the normal procedure for making chips is somewhere in Brazil or the US or Europe, there's somebody who designs a chip, and then they send the CAD files to some fab in Asia, and not quite clear where it is, and then the people there essentially fabricate, according to that design file, your chip. What they can do, and have been in fact known to do for cruder devices, is to add additional features. So for example, if Vlad gives me a design and I'm interested in keeping track of Vlad, of course I'll put a little thing into the chip that he wants me to build for him that will keep track of Vlad and send back to me what Vlad is actually doing, which I may or may not share with Dragana. And so this is perceived to be a big problem. So this is something that's had this has actually motivated partially motivated the U.S. side of the collaboration that I'm describing. So the question is, how do we get around this problem here, this destructive milling? And actually, there's a very elegant solution. But first of all, of course, the reason, of course, you think, well, a chip is this. It's this flat object, so why don't you just put that flat object in the beam and rotate it around? Of course, that flat object is very big, and so it'll absorb lots of X-rays. Of course, the reason we had that pillar being 10 microns in diameter was that was the distance that the X-rays could go, and is also well matched to the depth of field of the optics that we have, the X-ray optics. So if I give you, though, a 3mm chip and put it transverse to the beam, of course, it'll just absorb the beam. I won't get any information through. So there's a very obvious solution to this problem, which is shown here, which is actually you take your wafer and you just tilt it. Okay. And that's called laminography. And then actually but now you're in a even harder metrology problem than the one I defined before, because now things are no longer perpendicular to each other, and I'm rotating essentially around an axis which is at an angle, at an oblique angle relative to the incident beam. Because you're a physicist, they'll let you work out that the first thing is, of course, the moment that this is the phase space that you're accessing in angle, is you actually get yourself an interesting problem, information problem, in that the K space that you cover is no longer complete. You have actually something called the missing cone in reciprocal space. And this is an exercise you can give your students to see why. And so you cannot get a complete tomogram that way. However, of course, if you're clever at software, you can actually fill up that missing cone by some knowledge of the priors for the scattering experiment that you're doing. And so what we did was we developed both the mathematics essentially to solve this missing cone problem, as well as, of course, all of the mechanical engineering to now have a tilted geometry rather than a cylindrical geometry for the experiment. And here we go again. We've now basically built this rather elaborate machine to solve that mechanical problem. And then we got ourselves a chip. This happens to be a Taiwanese chip. We still just simply because of the fact, of course, that we don't have an industrial scale machine, we still cut out, but we simply cut out a plaquette here from this apple. There's nothing about this technology that wouldn't allow you forced to simply have a bigger machine, which would then just be more expensive to build. And then we again ran the algorithms on this, and let me just see. And here, what we can do is we can choose the area in the same that we're looking at, using essentially the same concept that we normally would with an optical microscope, namely the concept of zoom. But here the concept is implemented differently. The way you zoom is you just simply, the zooming is simply defined, the degree to which you can zoom is simply defined by the length of time that you count. And the reason that the zooming follows is that scattering at large angles tends to be smaller than scattering at small angles. But of course, it's the large angles that dominate the resolution. So the zooming operation simply is an operation where you count above the noise at progressively higher momenta on the detector, progressively higher scattering angles. And so simply by choosing where you look and count, it's where you put most of your X-ray counts, you actually can zoom in on a particular region. And so this is just showing you essentially a tour of this chip and various pieces of it. You're starting out here basically with this distance scale, 170 microns, and then we've decided we're going to go look at that little area over there. And then investigate. So there we've already got far more detail, because that's all of this high angular, high momentum stuff. And we can go inside and see essentially more and more detail. And what this particular circuit contained was actually one, and you'll see this in one special element, which it should show you momentarily, which is that inverter. There's only one inverter. There's only one needle in this haystack. There's one inverter in this entire chip. And we're able to find it. That's the circuit diagram, and that's the design file. So that gives you an idea of what the technology can do. Just a still picture. That's the thing we were looking for. It's there, and we can actually match up with the design file. And this shows essentially various sections, just making the comparison in greater detail than I just did, basically with just pointing at the images. Again, for a physics audience, this is an interesting plot. So we have a circuit, and what this zooming tool allows you to do is actually to inspect this circuit over 4 decades of design rules. Now, I remember at the beginning I said intelligence, both our intelligence or machine intelligence, at least of a certain complexity, is based on a hierarchy of features on a hierarchy of length scales. And it turns out actually that these peaks here are not noise, that these peaks here correspond to essentially different design rules that the different teams had for the different levels of this particular connectome. So starting off with the design rules down here, 22 nanometers, that's the design rule for the transistors. You move up here, this is then starting to be, this is still for the transistors. Up here you're getting to the standard design rules for the interconnects. And then going all the way up out. And so this is essentially just showing you how the zooming feature is such a powerful thing. This is also interesting. This is spatial period here. This is a logarithm. And you can imagine that using this technology also to deal with the types of materials physics problems that we've been hearing about at this meeting would actually also be very interesting. Good. So, of course, I've now just been focusing on artificial intelligence. Let me just show you that we have, of course, also been working with natural intelligence. And here I'm just showing you a tour through a section of brain. This is actually a study that was done to look at the pathologies associated with Huntington's disease. And those circles there you're seeing actually are basically axons. And this is just now just taking a movie, you're just going straight through this person's brain, and this is a segmentation here, and of the neurons, which you see there. Remember at the beginning I told you about vasculature. That's of course red in this thing, and then the neurons which are being fed by that vasculature are essentially showing up here in blue. There were actually comparisons then could be made between a normal undiseased brain and the diseased brain, and you can see these purple lesions here are forming on in this case, I'm sorry, it was Parkinson's that we were talking about. This case, this growth here is responsible, it seems to be associated with a motor neuron disease. And so there's a lot of course, I have to emphasize that these people were no longer alive, and they were not alive even before the experiment, so we were ethical. Now, of course, the Holy Grail, you'll notice the resolution here is much worse than the resolution I showed you for the dead matter, for the cold dead matter, for the integrated circuits. And in fact, the big challenge until about a year ago is we had not gone down to the synaptic level. But in the last year or so, the team at the Swiss Light Source, together with collaborators also at the Francis Crick Institute in London, have actually finally managed to start to get glimpses of the fundamental units, essentially the transistor of the brain. And here at the right is actually a full section. This is now a mouse brain. And in fact, these things here look like dendritic synapses. Of course, this is a very hot area, and it's interesting, of course, also here that with full correction, FibSem still looks a bit better, but the features that we're beginning to see here actually start to resemble the ones that are seen in sort of state-of-the-art FibSem measurements, which, as I said before, have a lot of disadvantages. Good. So I started off by telling you how much we know, essentially since we were in the Garden of Eden when we could just see each other, and all the way down optical microscopy, and then coming basically mainly with visible light, and then going through sort of classical tomography, and then how much we've learned since Bragg essentially saw diffraction from crystals, and various people, including Watson and Crick, saw diffraction from, well, Watson and Crick and Rosalind Franklin. Rosalind Franklin saw the diffraction, of course. They then took the credit, but that was an X-ray pattern coming up from basically reciprocal space. And what we've done here is actually to put the two and two together to fill up this, this gap, imaging gap. So we mix it, that's how we fill the gap. And the future really of this business, I think, is very brilliant. It's always interesting to reference things to Moore's law. X-ray production, the production of brilliant X-ray beams is actually the only technology I know of which actually is growing faster than computational hardware capability. This here shows you essentially computer speeds in megaflops per second. Here we've had essentially 12 orders of magnitude in 6 decades. X-ray brilliance just has gone up by 20 orders of magnitude and still going up very rapidly with the construction and commissioning of new machines like Sirius. So the future really is brilliant. I should also add that we did everything in 3 dimensions. Of course, we can move into the 4th dimension, the time dimension, of course, and the time analog of all of these interference experiments are, of course, things, again, you've taught in your freshman quantum mechanics courses. Those, of course, go under the name of the Ramsey effect, because remember the Ramsey effect is if I want to learn something about some 2-level system, let's say, and I just have a reasonably coherent beam of photons, and I can make perfect copies of that beam, then I can displace those perfect copies also perfectly with respect to each other in time. Then I can get essentially an infinitely good resolution on some dynamical system. Actually, this morning we heard some nice talks also about 2-pulse correlation spectroscopy, and of course that underpins that the concepts there are exactly the same. And the point is now we of course aim to do Ramsey experiments with X-rays at the same time that we're of course doing the imaging in K-space on the detector. And all of that, we are actually trying to do, we are actually planning to do with the free electron lasers, which produce not continuous X-ray beams, but pulsed X-ray beams. And so we just actually last year published a scheme to do that. You can read that at your leisure. So it all looks like we have one massive free lunch. Once we have the electron accelerator, we've paid for all of the interferometers and everything else. But I just emphasize again that the hardware is one thing, but the computer power is another. This shows another Moore's law. This is the exponential growth in the data mountain that we have just at PSI alone, coming from experiments of this kind. And it's just interesting to do to the back of the envelope calculation. That movie that I showed you is generated, of course, from a file, basically which is as big as about 1/10 the storage of a modern laptop. So the data we produce, that image file. So it's basically a feature film. It may not be quite War and Peace, but it's getting there. Now with the next generation of machines, including Sirius, where you go and have more stabilization, we're talking then basically in an afternoon or a few afternoons. This is just an afternoon here, or a few afternoons. In an afternoon, you're going to be generating 10 petabytes of data just to produce the image, to look for that funny extra feature of an integrated circuit. And this is actually comparable to the LHC annual data production. So we're actually producing a challenge here for your students, which I think is very worthy and very interesting. Oops, sorry. Okay, but if we sort all of that out, and I'm sure we will, because we are committed to building these facilities, is we'll be able to see basically both our hardware and our wetware have been hacked or are being hacked at the nanometer and femtosecond scale. So thank you very much.
Thank you. Time for questions.
So here's the question. I didn't know that people were actually hacking chips and trying to put a device there to spyware. But this is what comes to my mind. If you know, in the 80s, there used to be stealth fighters, stealth airplanes, which cannot be seen by normal radars, right? So since you're using this interference process and so forth to detect small things, you may imagine that you can design the geometry of this little device that you put in such that your machine could not see it. So there will be like a stealth spyware. So could you actually design something that could not be seen by your own machine?
I think it's certainly possible at visible wavelengths, because there's metamaterials. It's extremely, but you have to come up with a meta-atom. So if you can hack atomic physics to produce funny phase shifts for elements and also funny F-wave scattering and whatnot, at the angstrom scale, then you will win a Nobel Prize, in fact, for chemistry and physics, possibly theology. Yeah. So
yeah. I actually had two-part question. Mm-hmm. So the first one is that you said how much data will be produced, right? So we have to store that data. But the question is the rate that you produce that data too, right?
Yes.
Because how long does it take to get a scan with 1.5 nanometer resolution?
Well, it's going to take, we basically are, the thing that I showed you, the images that I showed you are between sort of roughly 15 nanometer resolution. We're doing actually better. There's new things that we're doing which are much better than that. But we're doing that at a rate which is, in 2 days, 2 or 3 days, you get that Intel file. And of course, with the brilliance, if you work it out, the brilliance of these fourth generation machines like Sirius, plus all of the improvements that we have in beam optics and so on, we're talking about 1/10 of the fourth increase in the efficiency. Then we have to work on the detector readout. Because of course these exposure, we're taking these small angle scattering patterns literally every few milliseconds. And then we have to start thinking, how do we download the detector? How do you download a megapixel detector? How do you download your camera at megahertz? And so all of these technologies, of course, have to come together. And of course, there's a lot of other people interested in such technologies. But this all has to work. But the reality is, it has been working until now. The detectors that we have now, we're moving already to our next chip, which is very much finer design rule than the one that I showed you. But at some point, it will stop because there'll be something that we'll be fighting localization. We'll be fighting. We'll be crossing over from sort of drift diffusion equations for our chips to worrying about Landauer-Bündner in the detector. So I think it's a cool area to be in. So, but you're absolutely right. There's limitations there on the bandwidth during the experiment, but the feeling is we have a technology roadmap forward.
And the second question is, well, it's not on the physics, but there's implications to intellectual property, right? Because now you can scan somebody's chip and copy, right? So yeah, it opens a can of worms. Right?
We didn't actually go back and try to cash in on the warranty. But we did, curiously enough, we did get but there's nothing they could do. I mean, there's nothing on that carton that says that you're going to be subject to a fine if you break the chip, which is we just broke the chip. And we happen, I don't think most people in their homes don't have the synchrotron.
So the technology is amazing, but I'm not convinced that having better visual images is going to teach us about intelligence. So I was wondering if maybe there's some other properties, like how the networks are related to each other, that might give additional information to the visual imaging.
Well, look, I mean, in neuroscience, I mean, the big deal now is to measure the connectome in the same way that the big deal was, 30 years ago to measure the human genome. And there was also, people were saying at that time, oh, what's a genome? It's just a map. It's not telling me about medicine. And at the end of the day, it turned out to be extremely important for modern medicine. You could not imagine modern molecular biology and modern medicine without the human genome. And the vast majority of neuroscientists believe the same thing. So there are many people working on it. Of course, the thing that one wants to do even more is functional connectomics, or basically functional brain imaging at the nanometer scale. Or actually, a lot of, when we talk to electronics companies, a lot of them, of course, like to do functional imaging of the integrated circuit. And so we have some ideas that we're thinking about. That's, of course, where the time dimension comes in. That's why I actually talked about the time domain. But you want to see, a lot of properties of networks follow from their geometry. That's something we learned from the condensed matter community, in fact.
Thanks.
More questions?
Just curious, did you manage to find this little chip that China infiltrate the Western community? That's number one. Number two, it seems to me that this is a very good business you guys should play with, right? I mean, people scare the government all the time to get funding, and that's how quantum computation and quantum information are basically sustain its own field. It seems to me that you guys can actually play the same game and get a lot of support to push the technology further.
Well, I mean, this was not free.
I know, but
Yeah,
I mean,
somebody paid for it.
to maintain this operation
yeah,
must cost a lot of money, right?
Yeah, to do this is, but there are people who, there was no problem finding the resources. Yeah. Yeah. This is, the lab is it's a large-scale engineering lab. And so if you count, there's of order, at some point, of order 100 people, not 100 people at the same time, but you realize the expertise that's involved. And, at the end, even for the software, there's a chain. There's a chain which involves, experimental physicists and more theoretical physicists, and then the computer guys who are translating the code, into run files on a GPU cluster that we have. So there's every aspect involves, expertise. There's, of course, far fewer authors on the paper, but then there's technical people and, of course, the people who maintain and manage the synchrotron itself. So this is the kind of thing for which you have a national lab. You can't do it in your, well, I can't do it in my kitchen simply. So, yeah.
All right. I don't see any further questions. No, there is one more.
So one thing I was curious about, you said that you can do the imaging of the brain and you can see the synapses forming in real time, seems like, right?
No, not in time.
Or not in real
Those
time?
are dead synapses. There's dead,
So that
dead
was
people,
my...
dead mice. Yeah.
Because apparently in modern medicine, they have put electrodes and they can see how you do certain things for people with traumas. Yeah. And the claim is that the brain actually forms synapses, so that's why they have permanent, it's not like Mr. Freud imagined that you just say it, your trauma, and it's gone, because the synapses has moved. And you may think if you can visualize this, then you can really cure many psychiatric problems.
That kind of image, there's at the sort of the millimeter level, there's incredible imaging technologies for neuroscience. This is basically going down the length scale hierarchy to the bottom. And that's really where, that's where the sort of one big part of the fundamental neuroscience community is at. but obviously, I mean, people would like to start with a molecular biology and build all the way up to intelligent thought or stupid thoughts, whatever. Yeah.
Any further questions? So if not, let's thank you again.